In the last two modules, we saw our first full run-through of a deep learning process using the MNIST dataset. Although it was pretty simple, we already saw the three main parts of a machine learning project. First, we began with data preparation using a dataset provided by Keras. We prepared the images by rearranging the 3D tensors into 2D tensors with shape, samples, and features. Then we normalized them to reduce the range of possible values to between 0 and 1. We also reformatted the labels for use later on. All these data munching steps were specific to the input and the output of this analysis, and we'll see some other examples of data preparation in the next case studies. In the second part, we defined our deep learning model. This involved three parts, which you're going to see in all the following case studies. First, we defined the model architecture using a series of layer functions. We can depict our model like this. Note the two activator functions, ReLU and softmax, that we also defined in the first part. Next, we compiled our network with specific loss and optimizer functions, in addition to a metric that is specific to our data, in this case, accuracy. Third, we trained our model with the fit function, where we defined the number of epochs and the mini batch size. So this is the framework of our model. Before we move on to the evaluation part, let's take a look at what actually happened when we trained our model. We went through 4 steps in our model. These 4 steps are the foundation of what we're doing in deep learning. In the first step, we drew a batch of training data and labels. In our example, we had 60,000 training samples, but we didn't test them all at once. We ran mini batches of 128 samples at a time. Again, just like the number of neurons in the hidden layer, the number of mini batches is going to be some power of 2. In this case, 128 is 2 to the power of 7. Second, we ran the network with, at the outset, random values. Remember all those 407,000 parameters? Well, we needed to start somewhere. So basically, all those parameters were just random values at the outset. It seems kind of weird, but it's actually a pretty good starting point. But what does it actually mean to run our network? And how did we use those parameters? To understand what happened, we need to take a detour into the world of matrix algebra. There are really only 2 operations that we need to know about here, the dot product and matrix addition. Let's begin with the dot product. Imagine that we have 2 matrices. One is 4 by 3, containing a grid of 12 digits, and the second is 3 by 1, containing a single column of 3 digits. It's important that the number of columns in the first matrix is the same as the number of rows in our second matrix. This is because we'll calculate the dot product of each row in the first matrix with each column in the second matrix. That means we'll end up with a matrix that has the same number of rows as the first matrix and the same number of columns as the second matrix. I'm going to generalize our matrices here. The operations are exactly the same, but I'm going to call the first matrix W, which stands for weights, and the second matrix is going to be called A0, which stands for the input or starting activation rules. We'll call the output A1. The indices are generalized with an N and a K. N signifies the number of columns in the input matrix, and K signifies the number of rows in the weights matrix. We can see in our generalization that the weights matrix is always going to have the same number of columns, n, as there are rows in the A0 matrix. That also means that A1 is going to be the same number of rows, k, as the weight matrix. We'll see how this comes in handy in a few minutes. Okay, so that's the dot product. It's not so bad actually. Matrix addition is even easier. Let's introduce another part to our formula. It's a matrix that has the same dimensions as the output from the matrix algebra, namely 4 by 1. We're just going to add the corresponding values to each other, so that's actually even more straightforward than the dot product. If we update our generalization, we'll just add another matrix in the end, which we know is going to be just as long as A1, which means k rows. So what do you think this has to do with our network? Can you guess what W, A0, B, and A1 are? Well, let's begin with n and k. Remember, n is basically the number of inputs, and k is the number of outputs. In the network, the first inputs, n, are the 784 pixel values, and the outputs, k, are the 512 values we'll get from the 512 neurons in the hidden layer. A0 is going to be the 784 values from the 784 pixels in each image. Remember from our diagram that every pixel value is connected to every neuron in the hidden layer. That's what we mean by a densely connected neuron. And now we can see what each neuron is. It's actually just a value in the weights matrix. How many rows do you think we have? That's k. There are 512 rows. Each of the 784 pixels is multiplied by 512 different weight values, one for each neuron. That means that every pixel can be multiplied by a different set of weights. Each row in the weight matrix contains all the weights connecting each input value to all neurons in the next layer of the network. How many parameters do you think that is? Well, 512 multiplied by 784 is 401,408. That's already a lot of parameters, but remember we had a bit more than that in our final network. After the dot product is calculated, we'll do an addition of the bias parameter. This is another 512 parameters that we have. The result is 401,920 parameters in the first layer. Let's remind ourselves what we saw when we looked at the summary of the model in R. The first dense layer had 401,920 parameters. Okay, so now you know where that value comes from, and actually, if you had the matrix, you can calculate all those values yourself. I want you to realize that although it looks pretty difficult, what we're doing here is actually pretty straightforward. Let's go back to an example I went through in the first unit. Remember our simple linear regressions? The formula for our model was beta naught plus beta 1 multiplied by some input value, x. It's basically the same structure as we see here. We have a multiplication and an addition, just that we have a lot of them because we have a lot of input values. It helps to think about our formula in this way, because we can more easily visualize a single formula than that massive amount we'll get from our neural network. This simple formula can define any straight line in 2 dimensions. Beta 1 defines the slope and beta naught the y-intercept. So what this tells us is that for each layer, we're going to end up with a matrix of outputs that is going to have as many rows as neurons. There is one last piece to the puzzle. For the purpose of deep learning, we're not just going to take those output values. We're going to make one more adjustment, and that's the ReLU activation function. Let's take a break and we'll pick up the discussion in the next unit.